Alright, so in this video we're going to introduce Dirac's delta function and the Heaviside function. Sort of before I give the definitions, I want to sort of try to motivate them, especially sort of the Dirac delta function, because it's a little bizarre at first, and if you don't have, at least a little bit of motivation, I think it can get a little confusing why we would even care about this in the first place. So to start off with our motivation, a 2 kilogram block sits on a frictionless surface, and at time t equals 1, a bullet impacts the block with an impulse of 10 Newton seconds. Assuming an instantaneous impact, can you find a function modeling the block's velocity, and then the same for its displacement and its acceleration? So first, let's sort of think about, Newton seconds. So, Newton, right, is a kilogram meter per second squared. And so 10 Newton seconds equals 10 kilogram meter second squared times second, or 10 kilogram meter per second. From this, if we divide by 2 kilograms, we see that the final velocity of the block sort of has to be 5 meters per second. So we can sort of write down a velocity function as a function of time. So before the impact at time t equals 0, let me give myself a little bit more space. We're just sort of assuming, but it says sitting, so it's not moving at all. After the bullet impacts it, it's going to be moving with a velocity, not of 1, sorry, but of 5 meters per second. Okay? Next, we're sort of asked to do the same thing with its displacement. So we can sort of see if we just kind of integrate this. Again, before time t equals 1, we're not moving. So we're just going to be sitting at the 0 position. If we integrate 5, right, we get 5t plus c. Because we sort of start moving at time t equals 1, we need to be at 0 still at time t equals 1, so we subtract 5. That's sort of solving for c. And our acceleration is a little bit weird, right? Acceleration is the derivative of velocity. And so one thing we can say about acceleration is, before t equals 1, it's got to be 0. After t equals 1, it also has to be 0. But at exactly time 1, right, it can't be the constant function because this is not really the constant function. So we sort of say it's, maybe infinity, but this is like very vague and, not very rigorous at all. So this is sort of a loose answer for the acceleration. Okay, so a lot of this stuff sort of has a special name. So the Heaviside function is the function where for t less than 0, we're at 0, and for t greater than or equal to 0, we are at 1. A lot of times we will use u subscript c to mean u of t minus c. And note that this is also going to be the same thing right? If t minus c is less than 0, then that means t is less than c. So we're going to be 0 for t less than c, and we're going to be 1 for t greater than or equal to c. So sort of keep these definitions in mind. The Dirac delta function, again, it's not really a function, but it's kind of the best answer for our acceleration. So we sort of say that we denote this with a delta, and we sort of say that this is, in a sort of loose sense, the derivative of the Heaviside function. And so sometimes it's sort of defined via the following sense. So phi of t equals 0 for t less than 0. It's also equal to 0 for t strictly greater than 0. And it's got to be, I guess, infinity at t equals 0, so that the integral from negative infinity to infinity of phi of t dt equals 1. Note also, this says that phi of t minus c is the derivative of u subscript t. Okay, so these are sort of our definitions, and it's really useful. So Heaviside function, I think, is more straightforward, but the delta function is, look, obviously a bullet's impact is not sort of sent to the block instantaneously, but for a lot of applications, we don't really care what happens, during that split, teeny split second when it does actually impact. So the Dirac delta function is like sort of a very convenient lie. We sort of assume the bullet's impact or some other very quick occurring thing sort of occurs instantaneously, and then it lets us sort of get an easy model for the problem at hand. So to sort of further motivate it and to sort of show where we're going, we're going to sort of apply these two functions to springs, or look at sort of some spring problems. So we have sort of the following setup. So a 5 kilogram mass is attached to a spring stretching it 70 centimeters. The spring is then stretched an additional 10 centimeters and released. So given that sort of background setup, we then have two different scenarios, and we want to set up IVPs, but not necessarily solve them yet. So suppose for the first scenario, at time t equals 3, a bullet then impacts the mass, and it has an impulse of 2 Newton seconds in the upward, meaning negative, direction. So let's go ahead and set up a problem for this. So first, we have to solve for k. Oh, and I should have specified, I forgot a word here. The spring is undamped. Right, so we have mass times g equals k times displacement, 70 centimeters. So plugging in mass of 5, a gravitational constant of 9.8, and k, and we'll convert this to meters, 0.7. Oops. We can just go ahead and see that k is equal to 5 times 9.8 is 49, divided by 0.7, giving us a k value of 70. Okay, so we have 5y double prime plus 70y, and we know stretched an additional 10 centimeters, so y of 0 equals 0.1, and released, so, meaning our initial velocity is 0. Okay. So we sort of have the background, but we still haven't set it equal to something. So we're not going to be set equal to 0 because we have sort of this outside force. So what we sort of do here is a bullet impacts at time t equals 3, impulse of 2 Newton seconds. So sort of what we do, right, this term right here is our force. And so what we sort of want to represent is we have an additional force acting on us 2 Newton seconds, and it happens only at time t equals 3. So that's going to be just 2 times delta t minus 3. So alternatively, at time t equals 5, a motor is switched on, which exerts a force of 2. It's a little hard to read. I'll rewrite that. 2 times sine t minus 5. So most of this setup is going to be the same. We don't have to resolve for k. And now we can sort of think, okay, what's our sort of additional force? Initial conditions are assumed to be the same. So for the motor force, right, if t is less than 5, there's no sort of additional forces. But if t is greater than 5, then we have this additional force 2 times sine t minus 5. So one way we could represent that is 2 sine t minus 5, but we want this to be 0 before time 5, so we multiply by the Heaviside function starting at 5. Right, so we can see here, you know, this term here makes the whole equation 0 if t is less than 5. But after that, we have the right value. So that's why a Heaviside function is really useful for stuff like that. Okay, so we've sort of set up our IVPs, but we're not going to go ahead and solve them quite yet. In fact, it sort of turns out that these are kind of a bit harder to solve than the general case. But it turns out that IVPs like this with discontinuous or even just piecewise solutions are actually maybe the best way to solve them is with Laplace transform. So you might have sort of been wondering, you know, why did we learn all this Laplace transform stuff just to be able to solve sort of questions we've already been able to solve, and a lot of sort of questions we've had, you know, kind of on the last exam. Well, one reason why is Laplace transform is a good way of dealing with scenarios like this, where you sort of have different sort of, you know, like a switch gets turned on or there's a bullet impact or stuff like that. Of course, to solve these with Laplace transforms, we're going to have to look at the Laplace transforms of the Heaviside and delta function. So to start us off, we'll start with the Heaviside function. Okay, so we can just sort of write down our integral. And let's, recall the definition just to sort of think about what's going to happen here. Okay. So the first case is what's going to happen if this a here is strictly less than 0. Well, for every positive t value, we're going to have that this is just equal to 1. And so we get that this is just equal to the integral from 0 to infinity of e to the negative st. And as we sort of saw, we've done this a million times. It's the Laplace transform of 1. Our answer is just going to be 1 over s for s greater than 0. Okay. The other case is if a, is greater than or equal to 0. And in fact, it doesn't actually matter if a is exactly equal to 0, the same sort of argument works. So we're just going to sort of focus on the case where a is strictly greater than 0. Okay, so if t is in between 0 and a, then u of at is going to be 0. However, if we're in between a and infinity, then we're going to get a value of 1. So we know what happens here. That's just going to be equal to 0. And here, let's go ahead and compute this integral. So we know, this is going to be the integral e to the negative st divided by negative s from a to infinity So this is still sort of similar to the previous case, but the difference is we're now plugging in not 0, but a. So for this limit to converge, we need s to be greater than 0, but then it's just going to go to 0, and we're left with minus negative s, so we can make that plus positive s. And we get that this is our Laplace transform. So to sort of sum up, remember, these are the same thing. Your lecture notes, I believe, only use the bottom notation, but the web work definitely uses the top. So if a is less than or equal to 0, then the Laplace transform is just 1 over s. If it's greater than or equal to 0, it's e to the negative as divided by s. Okay. So looking at our next example, we want to know what the Laplace transform of t minus a is. And again, sort of we want to note if a is, we'll use strictly less than 0 this time. Then we can just sort of say that, okay, well, phi of t is equal to 0 for all positive t, or really non-negative. And so this integral is just going to be 0. On the other hand, if a is greater than or equal to 0, then we're going to use the fact that this is kind of the derivative of the Heaviside function, and we can use the rule for derivatives. So, right, the Laplace transform of b of t minus a is equal to s times the Laplace transform of u of at minus u of a evaluated at 0. We're greater than 0 there, so we know that we follow the above rule, e to the negative as over s. And if a is greater than 0, then this is 0. And so we just get that our answer equals e to the negative as. Okay, so I sort of hemmed and hawed over whether or not to make this strictly greater than 0. The answer is what happens at exactly a equals 0. So sort of by convention, this is equal to 1, which, note, is the same thing as e to the negative 0 times s. So really, the case where a equals 0, the same exact argument doesn't necessarily apply, depending on because of how we defined our Heaviside function. But I want to be consistent with that with the lecture notes and the homework. But sort of by convention, the Laplace transform of the delta function is just 1. Okay. So one sort of thing that this says right, if I use the integral definition, means that somehow this integral is equal to e to the negative as. In fact, this is kind of a property of the delta function. So if you have A less than B less than C, then oh, nope, that should be C and that should be B. Then this integral is equal to f of b. Okay, so if we look back, we know the Laplace transform of the Heaviside function, we know the Laplace transform of the delta function. However, if we look back at sort of our starting, or one of our motivating examples, we don't need to just know about the Laplace transform of the Heaviside. We need to know what happens to the Laplace transform of the Heaviside times some other function. So we're actually going to look at what happens with this case where we sort of have u Heaviside function starting at a and a shifted function itself. So again, what we're going to assume that a is greater than 0 here. Otherwise, you're going to get just the Laplace transform of f of t minus a. Right, so on this first integral, the Heaviside function is going to be equal to 0, whereas on the second one, it's going to be equal to 1. So this is, of course, 0, and then we have plus the integral from a to infinity of f of t minus a times 1 e to the negative st dt. Okay, so what we are going to do next is multiply and divide by e to the as. So we can treat that as a constant for the purposes of the integral. So bring the top one in, and then we have e to the negative s times t minus a. So if I introduce a new variable here and call it x, say it's equal to t minus a, right? Dx is still just dt, but I'm going to change my bounds of integration. If t is a, then x is 0, and if t is infinity, well, x is still infinity. Oops, dx. And what I get is I just end up with the Laplace transform of f. So to sort of sum up, this is sometimes called, t-domain shift. If a is greater than 0, then the Laplace transform of f of t minus a times the Heaviside function starting at a is equal to e to the negative as times the Laplace transform of the unshifted version of f. I can state this differently. Where if I'm taking the Laplace transform of just this unshifted version of f, then I multiply by e to the negative as, and I sort of take the Laplace transform of f shifted in the opposite direction. And note, this needs to happen, in this case, if a is less than or equal to 0, then that term does not appear. You just get f of t minus a times u of a t is still just the Laplace transform of f of t minus a. Okay. Let's do a couple quick examples. So the Laplace transform of 5 times delta t minus, let's say, 2 is going to be 5 times the Laplace transform delta t minus 2, but that's just 5 times e to the negative 2s. If I want to compute the Laplace transform of, let's say, u to the t minus 2 times cosine of t minus 2, well, that's e to the negative 2s times the Laplace transform of cosine of t, right, using this t-shift rule right here. And so using the formula for cosine, I'm going to get e to the negative 2s times s over s squared plus 1. Looking at another example, we can have the Heaviside function ut plus 1 times e 5t. And remember, this is sort of a trick question because our a is negative, so it's just the Laplace transform of e to the 5t, which is 1 over s minus 5. And then lastly, we'll look at something like this. It's not obvious here what the shift is, or how this is somehow a shifted function, so we have to use the other rule, which says it's equal to e negative pi over 4s times the Laplace transform of sine of 3 times t plus pi over 4. We now have to use the addition formula, so that's going to be sine of 3t times cosine 3 pi over 4 plus sine of 3 pi over 4 cosine of 3t cosine of 3 pi over 4 is negative square root of 2 over 2. Sine of 3 pi over 4 is positive square root of 2 over 2. And if we pull out a 2 over 2, do that, we're going to get s over s squared plus 9, and then minus Laplace transform of sine over 3s squared plus 9. All right. So just to end it with some practice. So give those a shot. And let's go over answers. So for this first one, pretty straightforward. It's just going to be 2e to the negative 4s. For this one, note it's going to be equal to e to the negative s times the Laplace transform of e to the 3 t plus 1. E to the 3 is just a constant, so we can pull that out. And if we sort of simplify and expand, we get e to the 3 minus s over s minus 3. Over here, it's good to note that this is sine of 3 times t minus 5. And so this whole thing is just equal to e to the negative 5s times the Laplace transform of sine of 3t. And now that's just e to the negative 5s times 3 over s squared plus 9. And we will end it there.